6.5, Communicating across the network. So, we've covered how async I/O works, and a bunch of tools that can be used to manage the execution of multiple streams in the code. That's all great, but what about doing some actual I/O with it? The primary motivation for people to use asynchronous I/O is when writing network clients and servers, although that's certainly not the only possible use. So not only does async I/O make network communications efficient, it makes them easy. So we're going to look at opening a connection to a server and accepting a connection from a client on the server, as well as sending and receiving data in both directions. Here we have the code for a simple client-server pair of programs. They just read and write the same few bytes over and over, but they also serve to demonstrate everything needed to communicate across the network. There should be little about the client that is mysterious. It runs only a single task, which uses async I/O's high-level API to open a connection and then send and receive data through it. The server is able to handle many simultaneous connections at once. Because the start server coroutine we called launches a new task to run our serve coroutine each time a client connects to the server. Each task has the job of handling a connection for that single client, so the serve coroutine is almost as simple as the client coroutine. There's only a little bit of extra code to handle a connection reset error, which is the exception that gets raised if the client suddenly disconnects from the server, and a little more to handle the case where the request is an empty string, which the readline coroutine can only produce if the client has closed the connection in a less precipitous manner. In both cases, we want the server to stop worrying about that particular client, which we can do simply by returning from the client handling coroutine. The task running the coroutine finishes, and that's that. In the launch coroutine on the server, we called another coroutine called waitClosed. That pretty much does what it says. It waits for the server to be closed. Without that call, our launch coroutine would immediately terminate, and since we used run until complete, the whole program would terminate immediately afterwards. That would happen because start server launches off a background task and then returns, rather than managing the server directly. There's a low-level communication API that async I/O provides, but for the vast majority of cases, the lower-level API is unnecessary. Async I/O makes network communication simple. So let's just start the server and maybe a couple of clients and see what happens. So as you can see, it's running through the server loop and the client loop rather quickly. There's nothing really to hold them back except for the speed of network communications, which is not terribly slow, especially running on the same computer. But they work. They just send their data back and forth and keep track of how many times they've done so. A couple 100,000 times, no muss, no fuss, it works. Async I/O makes network communication ridiculously simple, at least in the common cases. We can use async I/O's open connection function to connect to the server, and we can use async I/O's start server function to create a server to handle client connections. If we pass a coroutine into start server, it automatically creates a new task to handle each client connection. If we pass a coroutine into start server, it automatically creates a new task to handle each client connection. In the next section, we're going to look at metaprogramming, which is, broadly speaking, having code that rewrites or reinterprets the code of our own programs.